So let's jump in and define what a matrix is. So we start by saying let M and N be any positive integers, 1, 2, 3, 4, whatever. Then an M by N matrix is a rectangular array of numbers arranged in M rows and N columns. So we write A is the matrix and it has components little a sub ij, where I indexes the rows, right? M rows, and I goes from 1 all the way to M. J indexes the columns from 1 all the way to N. We sometimes write it out just explicitly, saying A is equal to a square bracket of just what all of the components are. Sometimes people will use parentheses instead of a square bracket. Either one works as long as you use the same delimiter on both sides. Don't have square bracket on the left and a parentheses on the right, or a parentheses on the left and square brackets on the right, because that just looks weird. And let's see. Well, for mathematicians, our matrices do not move around much because it makes it difficult to calculate. So let's see some examples. Well, if you let x be a number, then a boring example is just the 1 by 1 matrix X, right? So let's think of an exciting example. Here's a 2 by 2 matrix that corresponds to rotation by 90 degrees to the clockwise. What are some other examples? Like one, I don't know, minus 17 pi cubed 0, 131, right? There's a matrix. So what is the dimensions of this matrix? That is to say, what's M and N in this case? Well, let's see. We should probably think about it like giving the height and weight. Height and weight. So how tall and how fat the matrix is, or how many columns it is. So how tall is it? It's 1, 2, 3 rows. And how fat is it? Well, it's 1, 2 columns. So it's 3 by 2. 3 by 2. I suppose we could give another example. Right. This is also well, I'm sure there's significance to it, but I'm just making up these numbers as I go along. What are its dimensions, though? It's like the previous one, height and weight. So how many rows does it have? 1, 2 rows. So it's 2 by 1 column, 2 column, 3 columns. So it's 2 by 3. So this looks nice, but we actually have a slightly more intricate taxonomy of matrices, just very slightly. So the first way we could get more interesting is if it's a square matrix. So an M by N matrix is square if M is equal to N. So, for example, well, we just saw one. It was minus 1, 0, 1, 0. That's a nice 2 by 2 matrix. We can consider a more complicated example. This is a 4 by 4 matrix. And we could come up with a 3x3 matrix. Those are all square. So what is not square? Well, this is an example of a not square matrix, right? Because it's not 3x3, it's not 2x2, it's 3x2. So this is not square. But these guys are square. The next consideration to make it more number-like is if it's diagonal. I actually don't know if we need m to be equal to n in this case. I suppose if you wanted to be completely general, you don't have to, but I can't think of an instance, for the life of me, of where a non-square matrix would ever be considered diagonal. So I'll just add that it's usually square. Not necessarily, but usually. So what are some examples? Are any of these guys diagonal? No. Why? Because if I is not equal to j, the component should be 0. That's the thing. The only guys that are non-zero in a diagonal matrix are, you guessed it, the diagonal. So let's see an example. They don't need to be the same value. So that's an example of a diagonal matrix. And we seldom write all the zeros out. So I could also do something like just leave them blank. Also diagonal. These square matrices which are diagonal are more number-like. We're seeing increasingly number-like matrices. So square is more number-like than non-square. Diagonal is more number-like than square. And now, even more number-like still is a scalar matrix. And that's a diagonal matrix if they're all the same value along the diagonal. So none of these guys are scalar. Boring example is this 4x4 matrix. It has to be 4x4 if it's a square matrix and there's 4 guys on the diagonal. But we could also do something, I guess, a little more exciting. They're all perfectly acceptable diagonal matrices, or scalar matrices. They're all diagonal, but only these guys are scalar. These guys are not scalar because they're different values along the diagonal. So this is a quick introduction to a taxonomy of matrices. And I should just say, like, if we were going to have a plot from most number-like to what in heaven's name is that? It would be scalar matrix be here, and close behind it would be diagonal. Then, I don't know, here it's a square matrix, and then over here, non-square matrix. And this is because when you have square matrices, we can define multiplying square matrices by each other. But we can't do it for non-square necessarily. So we'll get into that next time.